Welcome to one of the most exciting frontiers in machine learning, few-shot and zero-shot learning. Imagine teaching a child to recognize elephants by showing them just one or two photos, or even just describing what an elephant looks like without any pictures at all. This is exactly what we're achieving with modern AI systems, and it's revolutionizing how we think about machine learning. Traditional machine learning requires thousands or millions of examples to learn effectively. But few-shot learning enables models to learn new tasks with just a handful of examples, typically 1 to 10 samples per class. Zero-shot learning goes even further, allowing models to recognize and work with concepts they've never seen before, using only descriptions or relationships to known concepts. This mirrors human learning much more closely than traditional supervised learning approaches. The fundamental challenge these paradigms address is the data scarcity problem. In many real-world scenarios, we simply don't have large data sets. Think about rare diseases in medical imaging, endangered species in wildlife conservation, or new product categories in e-commerce. Few-shot and zero-shot learning make AI accessible in domains where data collection is expensive, dangerous, or ethically challenging. Let's understand the learning spectrum. Traditional supervised learning uses thousands of examples per class and learns task-specific patterns. Few-shot learning uses 1 to 10 examples per class and learns to generalize from minimal data. One-shot learning is the extreme case with exactly one example per class. Zero-shot learning uses zero examples of target classes but leverages semantic relationships and auxiliary information to make predictions. Meta-learning, or learning to learn, is the foundation of few-shot learning. Instead of learning a specific task, meta-learning algorithms learn how to quickly adapt to new tasks. The key insight is training on a distribution of tasks rather than a single task. Popular meta-learning approaches include model-agnostic meta-learning, or MAML, which learns good initialization parameters, and prototypical networks, which learn to create representative prototypes for each class. Prototypical networks are elegantly simple yet powerful. They work by computing a prototype, essentially an average representation for each class in the support set. During classification, they compare query examples to these prototypes using distance metrics in embedding space. Matching networks use attention mechanisms to compare query examples with all support examples. Relation networks learn to compute relations between query and support examples using neural networks rather than fixed distance metrics. Zero-shot learning relies on auxiliary information to bridge the gap between seen and unseen classes. Attribute-based methods use semantic attributes like has stripes, is large, can fly to describe classes. Word embedding approaches leverage pre-trained language models to understand semantic relationships between class names. Knowledge graphs provide structured relationships between concepts. The key is learning a mapping between visual features and semantic representations. Generalized zero-shot learning is more challenging and realistic. Unlike traditional zero-shot learning, which only tests on unseen classes, GZSL tests on both seen and unseen classes simultaneously. This prevents models from simply memorizing training classes and forces them to truly understand the semantic space. Domain shift and hubness problems are major challenges where models tend to classify everything as seen classes or get confused by high-dimensional semantic spaces. Large language models have revolutionized few-shot and zero-shot learning through in-context learning. Models like GPT-3 and GPT-4 can perform new tasks by simply providing examples or instructions in their input prompt. Chain of thought prompting enhances performance by showing the model how to reason step by step. Instruction tuning fine-tunes models to follow natural language instructions, enabling zero-shot task performance across diverse domains. Computer vision applications showcase the power of these approaches. Medical imaging uses few-shot learning for rare disease diagnosis, where collecting large data sets is challenging. Robotics employs few-shot learning for rapid adaptation to new environments and tasks. Wildlife conservation uses zero-shot learning to identify new species based on taxonomic relationships. Autonomous vehicles leverage few-shot learning for recognizing rare road scenarios and unusual objects. Natural language processing benefits enormously from few-shot capabilities. Machine translation for low-resource languages uses few-shot learning with limited parallel data. Text classification adapts to new domains and categories with minimal examples. Question answering systems use zero-shot learning to handle questions about topics not explicitly covered in training. Code generation models can write programs in programming languages with minimal examples. Evaluation challenges in few-shot and zero-shot learning require careful consideration. Episode-based evaluation simulates the few-shot scenario during testing by sampling support and query sets. Cross-validation across different task distributions ensures robust performance estimates. Statistical significance testing is crucial given the high variance in small sample scenarios. Fairness evaluation ensures models don't exhibit bias when generalizing to new classes or domains. The future is incredibly promising. Foundation models are enabling unprecedented zero-shot capabilities across modalities. Multimodal learning combines vision, language, and other modalities for richer few-shot understanding. Continual learning integrates few-shot adaptation with lifelong learning systems. These paradigms are democratizing AI by making machine learning accessible even when data is scarce. In our next session, we'll implement hands-on few-shot and zero-shot learning systems to see these concepts in action.